we're going to do a lot with the quantum numbers, so it's important that you know all the rules for all four quantum numbers, and you can look at a set and determine if anything violates the rules or not. So if we're given a set of four quantum numbers and we want to see is that allowed or is it not allowed, I would always start with the quantum number n, because n controls L, L then controls m sub L, and so if you always start that way, you can see if anything violates the rules. For the choice A, we start n is equal to 0, and right away that's not allowed, because the smallest value of n, remember, was 1. It can be all the way up to infinity, but it has to be at least 1. So quantum set A is not allowed. For set B, we start with n is equal to 3, and that's okay. If n is 3, remember L goes from 0 up through 1 less than n. So if n is 3, L could either be 0, 1, or 2. And we have to choose one of those numbers, and in this case the choice was made to make L is equal to 2. So that's okay. And now once we set L to be 2, we look at the choices for m sub L. And remember, the rule is m sub L goes from negative L through 0 up to positive L. Well, if L is 2, that means we have our choice of negative 2, negative 1, 0, plus 1, or plus 2. And again, we have to choose one of those 5 numbers, not all of them. And this time the choice was negative 1, which is one of the 5, so that's okay. And then the last quantum number, the spin, can either be plus 1/2 or minus 1/2. So choice B is a valid choice of 4 quantum numbers. We're going to do the same thing for choice C. N is equal to 4, so that's okay. If n is 4, then remember L starts at 0 and goes up to 1 less than whatever n is, which is 3, and so having a choice of negative 1 doesn't work. So A and C are not allowed. The only one that's allowed is choice B. So it's very important that you know those rules forwards and backwards so you can quickly tell whether the quantum number is allowed or whether it's not allowed. Remember, the quantum numbers are related to these mathematical functions, and we're not going to go into the detail of the function, but we're going to look at what those functions, what shape they have. Different orbitals have different shapes. And physically, it's based on the probability of finding an electron. So this diagram shows what would happen if we made a graph, if we put a little dot on our three-dimensional coordinate system every time we found an electron in a certain orbital. And it turns out that this was the orbital when we have the quantum number n be the smallest it can be, which is 1, and then the quantum number L, if n is 1, the only thing that works with the rules is L has to be 0. And then m sub L goes from negative L through 0 through positive L, so we only have one choice, which is 0. And then the spin has to do with the particular electron, which we'll go into more detail later. But for this given orbital, if we put a dot everywhere we find the electron, over time we'll come up with a spherical shape. So remember, this type of orbital was the type that had the quantum number L equal to 0, and we call that an s orbital. There are other s orbitals in an atom where n may not be 1 anymore, n might be 2 or 3 or 4, but they would also have the same spherical shape. If we increase our quantum number L to 1, it's no longer called an s orbital, now it's called a p orbital. And if we did the same sort of three-dimensional plotting, we'd end up with a dumbbell shape. Those are the only two shapes that you need to remember, spherical and dumbbell shape. The other orbitals, if L is 2 or 3 or higher, the shapes become more and more complicated, but we're not going to expect you to remember those other shapes.